Hello again, everyone. So in this video, we're going to be talking about vector spaces again, because I know how much everyone likes vector spaces. So what we've done so far on vector spaces is we've covered the sort of the most common vector space, really, which is Rn. And of course, n could be really anything. It could be R2, which we usually know as the vector 2, 1 in the xy plane. So if I have my xy plane here, if I have x and y, and I have 1, 2, and 1. So my vector 2, 1 in R2 is actually just, I go to the right 1, 2, and then I go up 1 here. So this is 1. So that's how you would represent your vector in R2. But then if you get to higher levels of n, so if you get to, let's say, R5, well, it's not really possible to represent these visually. You just have to think of them as having 5 components. So 1, 2, 3, 4, 5 components. And this could be arbitrarily big, so it could be R536, really. Okay, so it can be anything you want. Then we also covered the vector space of polynomials. So we talked about P and R. Again, the n is pretty arbitrary. So if I were to say P3R, then an example of a vector in P3R could be x plus 2x squared, plus 2x cubed plus root 2 x squared. So my highest degree here is 3, and so my highest degree corresponds to the 3 here. Okay. But this could actually be a vector in P4R or P5R, because this just states how high your degree, how big your degree can be. Okay, so that was another vector space we talked about. The last big vector space in linear algebra, well, I mean, there are a lot, but this one you'll see quite often, is the vector space M, so capital M, M by N R. Okay, and informally, what this is, what we refer to this, is, so we say that this is the set of M by N matrices. So this matrix has M rows and N columns. So the set of M by N matrices with real entries. Okay, so that's where the R comes in M by N R. Okay, so more formally, we can write this using a pretty big matrix. So the very first entry, the 1, 1 entry, I'll call A11. And so the next one, the one to its right will be A12, because we've shifted columns. And then down here it'll be A21, and then this will be the same until AM1, and this will be the same until A1n. And then on its diagonal, we could have AMN. Okay. And what we typically say is, we say that it's this matrix such that A11 through AMN belong to the real numbers. So all of its entries are real. Again, if this R here was, say, Z, right, which is allowed, you would have to say, okay, well, it's the matrices with integer entries, not real entries. Okay? And so how do we define our basic operations in M by N? Right? So our basic operations. Okay, so we have, remember, we have vector addition, vector addition. And we have scalar multiplication. Okay. So if I say A plus B, right, where suppose A and B belong to M by N R, then A plus B, by definition, we just said that if something belongs to M by N, so if something belongs to this guy, then it'll look in general like this. It'll look more or less like this kind of matrix, okay? So that's how I'm going to write it out. So my A is going to look like, let's use blue for my A. So my A is going to look like A11 through A1N, and down here AM1 through AMN, okay? And then let's use red for my B. So I'll have plus, and then B11 through B1N, and BM1 through BMN. Okay, so this is just, I'm just generally representing how my vectors would look like, my matrices or vectors would look like. Okay, so when you add them, what really happens is you take the 1-1 entry of A and you add it to the 1-1 entry of B, and then you take the 1-2 entry of A and add it to the 1-2 entry of B, and so on. And then the 1n entry of A to the B1, the 1n entry of B, and that happens for every single entry of A and B. Okay, so what happens is you get this matrix, you get so this is an equals, this is an equals, so you get the matrix. Okay. So you get A11 plus, and you'll get B11. Okay. And this happens until you have B1N plus A1N, and down here you have AMN plus BMN, and then here you have BM1 plus AM1, right? Because this is AM1 and this is BM1, so you add them together, and that doesn't really look like AM1, so I'll read AM1. Okay, so my matrix is a bit it's overflowed with entries. Okay, and that would be your definition. So this is your definition of A plus B for M by N. So this is vector addition for matrices in a general vector space. Okay, what about scalar multiplication? Well, scalar multiplication is also pretty intuitive. So if, suppose you take, we take C belongs to the real numbers, and again we take A belongs to M by N R. Okay, then if I do C scalar multiplied A, then what this is going to give me, really, is, because we know that this is actually A11, sorry about that, we know that it's A11 through A1N, and down here it's AM1 through AMN, and so on. So what happens when you have a C, it sort of multiplies, well, it doesn't sort of, it does, it multiplies each entry by C. So C times A11, C times A21, until C times AM1, and then it goes to the second column, and the third column, and so on, until it gets to here. Okay, so that's basically what I'm going to write out. So it's equal to the matrix. So this is my result. So it's equal to the matrix C times A11, and this goes on until C times A1n, and down here we have AM1 multiplied again by C, and then to the right I have C times AMN. Okay, and this happens really everywhere. I just use the bounds to show that it's so at the most, if it happens at the most extreme points, then it happens everywhere, really. Okay, so that's how you define vector addition and scalar multiplication for m by n. And then, of course, to show that this was a vector space, you'd have to prove axioms 1 through 8. So the proof for each axiom is quite similar. Maybe I'll just set you up. I'll give you a setup for axiom number 6. So for axiom, why is my phone not working? For axiom 6, let me just remind you what axiom 6 says. So axiom 6 says that for all scalars a and b that belong to the real numbers, so that belong to R, and for all vectors u that belong to my vector space, a times b scalar multiplied u is equal to ab scalar multiplied u. Okay, so I'll just give you a setup for how you would show this for matrices. So my setup would probably be suppose A belongs to m by n R. So as soon as you write that something, in this case A belongs to m by n, you have to think of what that implies, what it means for A to belong to m by n. Well, if A belongs to m by n, that means that A can be written as a general matrices that looks like a general matrix that looks like A11 through A1n, and then down here AM1 through AMN. So that's what it means for A to belong to m by n, and then it has the two properties of vector addition and scalar multiplication that we just saw. Multiplication. Okay, so suppose A belongs to m by n, and C and B are scalars. So what you want to do, what you want to show is you want to show that if you take C times B A, then that will equal CB times A. So how you're going to go about doing this, well, I mean, if you want to go about proving this, is you're going to expand this. So you're going to expand this as what it really is. Right?
All right,
so,
sorry about that. Someone was at the door. Okay, so as I was saying, you have C times B times A11 through A1n, and then down here you have AM1, and then over here you have AMN, right? So then what you would want to do is you'd want to get something that looks like, so you want to get to something that looks like CB times A11 through A1n, and down here AM1 through AMN, and then over here, so that's what you want to get at, right? So then what you would do is you would first multiply each entry by B, okay? And then you'd get a new matrix. So you'd get C times B A11 through B A1n, B AM1, B AMN, okay? And then again you would multiply by C, so you get CB A11, and then similarly everywhere, really. And then what you could do is you could factor the CB out. And you would get what you were looking for, which was CB times A11 through A1n, AM1, AMN. Okay. yeah, here it was lazy, but like it's the same thing everywhere, and that's equal to CB brackets A. Okay, and the reason why is because over here the operation is over the real numbers, and so if the operation is over the real numbers, then you know that x, y, z is equal to xy times z. So that's basically what I did. I just factored out C and B from every entry. Okay, so I did that quite rushed. Sorry about that, but that's basically how you prove that kind of axiom, and then similarly for all the others, and then you of course have your vector space. But regardless, that was the vector space I wanted to talk about, was M by N, which is, you know, all of the vectors that look like this guy. All right.